Hello guys, welcome on Tesla Adventures. In this video, I'll be starting surface tension, and I've seen in my teaching career that surface tension is not a comfortable topic for most of the students, as this is never explained to them in the greatest depth. And in this video, I'll be going in this playlist complete, I'll be going in the greatest depth of this chapter, and the surface tension would be your strength, like the mechanics is the strength of most of the students after you follow this playlist completely. So let's start this video and let us discuss the basics of surface tension. So first of all, we know that there are two types of van der Waals forces. One is cohesive and other is adhesive. So we know that cohesive force is the weak van der Waals force which is acting between the molecules of same material, while adhesive force is the weak van der Waals force which is acting between the molecules of different materials. For example, if we paste Fevicol on a wooden board, then we can see that let us draw two wooden boards. This is one and this is one, and we have pasted some Fevicol between them. So what is happening in between them on microscopic level is the fact that this Fevicol molecules are attracted by the wood molecules by adhesive forces, and this molecule, which is just attached with the wood surface, is being attracted by its neighboring molecule by cohesive forces. So in equilibrium, this cohesive force and this adhesive force is equal. And on the other side of the on the other plank, on the other wooden ply, this same thing is happening. So by this, these two wooden plies are binded together by using adhesive or Fevicol. So this is the cohesive and adhesive forces, and we have already discussed the cohesive forces in viscosity also. Now we know that viscosity or viscous force is in the flowing liquids, but here the surface tension is in the liquids which are not flowing and which are in rest. Now I'll be discussing this thing in detail. Now first of all, let us see that let us draw a diagram of a liquid contained in a container, and this liquid has many molecules, and some of the molecules are also situated on the surface of the liquid. Now let us imagine a molecule which is inside the liquid in some depth. So this molecule is being attracted by all the neighboring molecules by cohesive forces, and the net cohesive force acting on this molecule is 0. So it would be at rest, obviously. But this is not the case with the molecule which is on the surface of the liquid, because on the surface of the liquid, these molecules do not have any molecule over them. They only have the molecules in the level of them or below them. So we can say that from all the direction on the surface, the cohesive force is acting on this molecule. If I draw a diagram, let me show you a diagram. Let us delete this thing. So if I draw a top view of this diagram, this is also a top view, but this would be used in some other perspective. Let us draw another top view. So if this is the top view, and this is the liquid. So if we consider a molecule like this is a molecule. So we can say that this molecule is being attracted by cohesive force acting on it from all the sides on the surface, as well as some molecules which are below this molecule inside the liquid are also attracting this molecule by cohesive forces. So obviously a net force is always acting on this molecule in the downward direction, but it never goes down, because we'll be discussing this thing in detail. But first of all, let us discuss the fact that cohesive force is the force acting between the molecules of the same material, and the adhesive force is the force acting between the molecules of different materials. And here we are discussing the surface tension, which is due to the cohesive forces only. Okay, and we have to also imagine the fact that if we talk about the cohesive, the numerical value of the surface tension, I'll be telling you in this video that what is surface tension. I have not explained this fact till now, but I'll be telling you that what is surface tension. But first of all, let us discuss that what is the numerical value of surface tension. So actually you can imagine imaginary line. Let us suppose an imaginary straight line. Okay, you can imagine a line like this also. This is no problem. So I have imagined a straight line for ease of calculation. So this is an imaginary straight line, and these are the molecules which are situated on this straight line. We all know that the net force acting on these molecules on the surface is zero, but obviously some forces is acting on them in the downward direction. So if we just consider the forces acting along the surface in the one side, let us consider that the cohesive force acting on these all molecules in this side only is Fc. Obviously the same amount of force will be acting in this side also, and therefore the net force will be zero. But let us talk about the net cohesive force along the surface acting in one particular direction. So this Fc is the net cohesive force acting on these all molecules in this direction only along the surface. And this force per unit this length is called as surface tension. So this is the numerical value of surface tension, and numerically surface tension is force per unit length, and hence its unit will be Newton per meter. Okay, and obviously this surface tension, due to this surface tension, you can imagine that all the molecules are, if I again draw this diagram, so you can see that, let us draw the liquid again, and if I draw all the molecules, some of the molecules like this, okay, so these molecules will be experiencing the cohesive forces in all the directions. I cannot draw all the molecules, but just imagine some of the molecules. Okay, so each molecule is experiencing a pulling force applied by the neighboring molecule on it, and due to this fact, this surface of the water will be of liquid will be behaving like a stretched membrane or a thin film, and this film behavior is called as surface tension. So surface tension is actually the property of a liquid at rest, by which that liquid free surface behaves like a stretched membrane, and it always tends to minimize its area. So this property of that liquid which is at rest is called as surface tension. And I'll be explaining again that why I'm saying that it is tending to minimize its area. Okay, so this is the first basic of the surface tension. You can take the screenshots of these theories so to create your notes, and let us move forward. Now, why we are saying that surface is tending to minimize its area? Now just imagine that you are in a square room, and you have a square shaped polythene or plastic sheet which you have pinned in the room at a height of h by 2, where h is the height of the ceiling. So just imagine that you have nailed that plastic sheet tightly at a height of h by 2 in the walls of the square, and therefore there will be a plastic film of the area of the face of the square formed at the height h by 2 from the floor. So you can imagine that each molecule on that film will be experiencing some pulling force from all the sides, and hence we can say that this film will be behaving like a stretched membrane. Okay, now if we place some heavy weight on that film, let us imagine that we have placed some brick. So this film will bend down to an extent, and the molecule on the film will not go down because the net force acting on the brick, which is mg in the downward direction, will be balanced by the two components of the cohesive force. You just imagine that this is a molecule and this is the other molecule, and these molecules are pulling this molecule by cohesive force, which I have denoted by tension in this case. So the component of tension in the upward direction 2t cos theta will be balancing mg. And now if I have increased the weight and I have placed one more brick on that sheet, then it will bend to a larger degree, and again 2t cos theta, now theta is different, will be balancing the mg. And eventually, as I keep on placing the bricks one on one on that sheet will either at some point of time that sheet will either break, or all the nails of the sheet will be removed and sheet will get down on the floor and it would be getting folded, or the area of the sheet would be less than the area when it was nailed. So obviously this same thing is happening in the liquid, that each molecule has a net force acting in the downward direction, but it is not going in the downward direction because when it goes to a smaller angle in the downward direction, then the components of the surface cohesive force, component of the surface tension, balances this net force in the downward direction, and hence molecules is prevented of going down. But it has a tendency of going down because net force is acting in the downward direction, and due to this tendency this molecule is always this surface of the liquid is always tending to minimize its free surface area, and this property of the liquid is called as surface tension. So finally, let me again tell you the definition of surface tension, according to which surface tension is a property of a surface property of a liquid which is at rest, by virtue of which the free surface, now free surface means surface which is in contact with air, the free surface of that liquid behaves like a stretched membrane, and it always tends to minimize its free surface area. This property of the liquid is called as surface tension, and this surface tension arises due to the cohesive forces acting between the molecules of the liquid. And this obviously, as name suggests, is a surface phenomena. Surface tension does not occur inside the liquid, because you can imagine that any molecule which is inside the liquid will be having zero force acting on it, in fact zero net force acting on it. Okay, so surface tension does not occur inside the liquid, it is a surface phenomena, first of all. Now let's move forward. Now obviously, as I told you, that surface tension is a property of the liquids which are at rest, because all the molecules which are holding each other together are forming a film, and to create a film these molecules should be stably placed on their positions. But if the liquid starts to flow, then these molecules move on the surface randomly here and there, and therefore there is no fixed stable position of their holding together, and therefore we can say that there is no surface tension developed on this flowing liquids. So we can say that surface tension dominates on the liquids which are at rest, and it is very negligible inside the flowing liquids. As well as we also know that viscosity is also a result of cohesive force, but viscosity is dominated in flowing liquids, because viscosity majorly occurs when liquid molecules are moving relatively to each other. But in the case of surface tension, it dominates in the liquids which are at rest. Now, what is the effect of temperature on the surface tension? So, let us imagine that if we increase the temperature of any liquid, then obviously, due to the thermal kinetic energy, the molecules of the liquid will be moving here and there randomly, and due to their movement, they would not be able to hold each other together, and therefore surface tension will decrease. So we always believe that surface tension always decreases by heating the liquid. And you must have observed the soap action of soap, which is sodium acetate ions, and you have studied in 10th class, I guess, that in dirt action, some of the soap molecules attract the dirt of the cloth and they remove the dirt from the cloth. So when you wash the clothes in with water, then obviously there is a film of water formed on the surface of the cloth, which prevents that soap molecules to go inside the cloth and to attract the dirt and to remove the dirt from the cloth, because that film prevents the molecules to go inside the cloth. So to decrease the surface tension, we always prefer to wash the clothes in hot water. So you must have seen in the winters, we always wash the clothes in hotter water, and this is the fact that the surface tension of the hotter water decreases. As well as you must have seen that when we wash the clothes, we dissolve some soap solution or impurity in the liquid. This is to serve two purposes. The first purpose is to provide the necessary amount of soap for performing the dirt action, as well as dissolving the soap or dissolving anything in water will decrease its surface tension, because obviously surface tension is the result of cohesive forces acting between the two molecules of H2O, if we are talking about the water. So the surface tension is the result of the cohesive forces acting between the two surface molecules of H2O. But if you will dissolve some impurity in water, H2O, then the molecules of that impurity will take place the place of the molecules of H2O, and they will displace the H2O molecules, due to which cohesive force will be decreased. And due to this decrease in cohesive force, the surface tension of the liquid will decrease. So obviously the dissolving of any foreign impurity which is dissolvable, I am talking about dissolvable, because if you throw the stones in the water, then stones are not dissolvable and they will settle down at the bottom of the water, and that will not alter the surface tension. In fact, surface tension will be altered only when you will dissolve some of the dissolvable impurities in the water, which will displace the water molecules, H2O molecules, and they will decrease the cohesive force and the surface tension will be decreased. But there is an exception to this thing, that when we dissolve rock salt, NaCl, which is an ionic compound, then the surface tension increases. This is due to the fact that when NaCl is dissolved in the water, then obviously Na plus and Cl minus are splitted apart from each other, and the hydrogen and H2O molecules are creating bonds with both of them. But they will decrease the cohesive force, obviously, because they have displaced the H2O molecules, but they are attracted to each other. Na plus and Cl minus are attracted to each other by a strong force, which is electrostatic force. So on the first attempt, we can see that the cohesive force between the molecules is decreased, but they have compensated that cohesive force by a stronger force, which is electrostatic force, and electrostatic attractional force will create a stronger chain on the surface of the liquid. And hence we can say that on dissolving any ionic compound like NaCl, rock salt, the surface tension of the liquid will increase. So this is an exception to this thing, but otherwise, on dissolving any non-ionic compound in the liquid, the surface tension will decrease. Now let us also imagine the fact that when we blow out bubbles from this ring or from this square, then the bubble formed is obviously spherical. The bubble formed from the ring is also spherical, and the bubble formed from the square shaped ring is also spherical. So the bubble is always spherical, and this is due to the fact that bubble always tends to minimize its free surface area due to the surface tension. Because bubble is what is bubble? Bubble is a thin layer of liquid which is containing some soap, and it has the air inside it and the air outside it. So there are two free surfaces. One free surface is this one, and one free surface is this one. And this is the thin layer of liquid solution between them. So the surface tension acting will be on the both sides of the surface. So due to this surface tension, this film always tends to minimize its area, and we know that for equal volume, the sphere has the minimum area. If you imagine a cone or a cube or a cuboid or a sphere of equal volume, then we can say that the area of surface of the sphere will be the minimum. So therefore, bubble which is blown by any shape of the ring will always be spherical. Drop is always spherical, but the sphere of the drop, which is somewhat distorted due to the gravity, but otherwise in the gravity free space, drop will always be spherical. Okay, so this was this thing. Now again we can see that we can imagine this is a U-shaped frame, and there is a moving wire on this frame. This complete arrangement is immersed in a liquid solution which is containing some soap. And you also must have imagined that we always can blow the bubble from the soapy liquid. We cannot blow the bubble from normal water, because in normal water surface tension is so huge that it would not allow that film to make a bubble. But in soapy water, surface tension is decreased due to the dissolving of soap in that, and therefore it easily allows the film of the ring to be formed as a spherical bubble. So let us imagine this U-shaped of wire, and there is a moving wire on this one, and there is a film of soap. Now if you see this soap film from side, then this is the side view, and there are two free surfaces on this soap film. The first free surface is above it, and the second is below it, because air is in contact above and below both of the parts. Now obviously we can say that cohesive force will be acting on both of the surfaces, and therefore the net cohesive force will be 2T into L. So in that case of two free surfaces, we would be taking the surface tension as 2T. It would give us the net cohesive force acting on that. Okay guys, now let us discuss a simple case of surface tension. So just imagine this shape of a frame, wire frame, and this is dipped into a soap solution, and this is the liquid film. And this is the coordinate of this point is x2 comma y2, and the coordinate of this point is x1 comma y1. So we just imagine a small now what we have to do, we have to find out the surface tension force acting on this wire frame, this one. On this frame we can easily calculate the surface tension force, but we have to find out on this wire frame. So let us imagine a small element of length dl, and we can see that this molecules of this wire will be attracting the molecules of liquid by small adhesive force, which is balanced by the cohesive force. So we'll be just drawing only cohesive force. Okay, so this will be the same thing. This is df. and this angle is, let's suppose, theta. So the component of df in the downward direction will be df cos theta, and this component will be df sin theta. Okay, and df will be equal to, let us imagine that there are two free surfaces above and below this liquid film. So surface tension will be 2t and the length is dl. So this is df, and dfy will be equal to integration, or we can say that fy will be equal to integration of df cos theta, and the value of df is 2t dl cos theta, and this is fy. And dl cos theta is, you can see that this is dl, this is dl cos theta is dx, this is dl cos theta, and this is dl sin theta. So we can write it down as fy is equal to integration 2t into dx, and 2t is constant, so fy will be equal to 2t into x2 minus x1. The integration of dx will be the length of this wire. Okay, and similarly fx is integration of df sin theta, and df is obviously 2t into dl, and dl sin theta is dy, so this is 2t into dy, and this 2t, and the integration of dy will be y2 minus y. So we can say that the force acting on this wire frame can be easily calculated in y direction by multiplying the surface tension with this length, and in x direction by multiplying the surface tension with this length. This is simple technique, and this can also be done by the fact that if we draw the free body diagram, we can say the net force acting on these wire frame is 0 because film is at rest. So we can say that the f vector plus fy vector plus fx vector is 0. So f vector will be counterbalanced by fx vector and fy vector. So the net force acting on this wire frame will be numerically equal to the vector sum of fx and fy by equilibrium method. So this was it in this video, and in the next video we'll be bringing some more concepts of surface tension. Thank you guys.